Okay, so this week we'll have a look at the object model. So lecture's basically divided into three different sections. I'm going to talk briefly about, or we'll have a little chat briefly about real-world objects, what they are, how you identify them, that sort of thing. Then we'll go into the sort of concepts or ideas that underlie the object model itself. There's five sort of fundamental concepts that the object model is built upon. And then finally, we'll look at how objects are implemented in the Python language. An object in a Python happens to be, the object in this case happens to be an alligator. Why Python? Why am I suddenly throwing you Python at you? It's because there isn't, or I haven't managed to locate, an easily usable, accessible, free object database. So if anybody comes across one that might be useful as a teaching tool and as a demonstration of an object database, I'd really like to hear about it. But it's relatively easy to implement objects in Python. How many people have done Python? Anybody done Python? One, two, a couple. You don't really need to do much Python for this. And the practical, we've got a practical this afternoon in which we'll play around with Python. And Python's dead simple, so hopefully it will work all right. But objects, so it's easier to actually use objects in a programming language than it is a database environment at the moment. But I'd love to find a database, an object database that could be used in a practical. Okay, so let's just have a little. So objects in the real world. Here's a high street. I don't know where it is, but what objects can we see? Can we just shout them out? Let's have a whole list of objects. Shops. Statue. Yeah, statue. Street furniture. Now, what is street furniture? Lamps, bollards, street furniture. Yeah, sort of drain covers, all sorts, manhole covers, all sorts of stuff like that. Yep. Anything else? Sorry? Buildings. Yes. What's the relationship between buildings and shops? Subclass. Yeah, some buildings are shops, some are multifunctional. Anything else we can see there? Sorry? People. Yes, people. We know what objects are. They're everywhere. Okay, and we've met objects very briefly. As I said, we sort of touched them in passing along the way. And I think we've met this concept, can't remember which lecture it was, the idea of instances and the idea of classes. So an instance is a specific individual object in the world, or thing in the world. So Waitrose, 15A, Claremont Raids, Surbiton, is a specific branch of a supermarket that happens to be in Surbiton. Streetlight number 163/30, invented number, is a specific street light in a particular place, particular time. Picture of the Fortingal U in Perthshire. It was in the news the other week. I don't know whether you heard about it. It's decided to change sex after about 2,500 years, I think, of being male. It's decided it's going to be female for a while, or part of it has decided, changed its sex. It was in the news the other week. So a particular tree in a particular place. And we group human beings to understand the world. We group these particular instances of things into classes, into groups based on similarity, some kind of similarity. So we can group things into things. So things like Waitrose is a member of the class shops, but it could also be the member of the class we call retail establishments, or a member of a class we call businesses. The Fortingal U might be a member of the class trees or a member of the class vegetation, depending on how we want to define our classes, and we'll talk about that in a minute. So the fundamental thing here is instances are individual things in the real world, particular things, and we can group these into various classes. The classes that we choose, because there are different classes that we could come up with. We could come up with shops, or we could have a business class, or a retailer, we could call it. Define a model or a view of the world. The classes that we select and choose represent a particular aspect of the world, a particular view on the world. And there are many views possible onto the world. So for example, that town centre, a view, we might be a town planner with a view. We've got a town planner here. He could tell us the town planner's view of the world. It presumably involves things like designated areas, conservation status, whether you're moving your advertisements too far onto the pavement, I don't know, things like that. The town planner, is there a good balance between retail premises in the area? I imagine a town planner is interested in things like that. Then there's the maintenance staff view of the world, look after the beds, the vegetation, sweep the streets, clean the graffiti, perhaps that kind of stuff. And then perhaps there's the marketeer involved in promoting products. Where is the best place to set up my pop-up stall to advertise my latest broadband deal or something like that? So different people have different views onto the world. So which classes we select define our model or view of the world. And there are these different views on the world. Each of these views have a purpose, generally. They're from a perspective. They have a reason for that view. And all these models, all these views are, by definition, simplifications of the world. Because we're dividing the world in a particular way, that is, by definition, sort of simplifying that world, because it doesn't include the complexity that the other views might represent. And here's one of my favourite quotes. It's a very well-known quote. You may have seen this before. All models are wrong, but some are useful. This is George Box. George Box, most of you might have, well, you may know of George Box, but not know what he's famous for. He's famous for the box plot. He invented the box plot for displaying graphical data, or the graphical presentation of data. So all models are wrong, but some are useful. How we divide up the world, however we divide up the world, we're making it simple, and by simplifying it, we're effectively making our model wrong. But nevertheless, that doesn't really matter as long as it's useful. Just a little drip into a bit of philosophy. So how we divide the world up and what the things that we identify in the world from a particular perspective is called an ontology from a philosophical basis. So ontology is the study of the nature of reality and the components of which it is composed. So the different ways that we divide up the world into different classes is defining an ontology, a way of understanding the world. And because in a computer, you have to fully define things in a computer, creating a model of classes, dividing up the world, provides a formal defined model, a defined ontology of the world. So there's loose ontologies, the way a town planner perhaps understands the world in his head, and then there's a formal ontology, the way that representation is put into the computer and formally defined in a computer. And the classes in a model are a form of ontology. As I say, we can have alternative ontologies of the same aspect of the world. And there are two ways in which ontologies can differ. One we've seen already is the set of classes that are defined. is our class, are we defining a class called shop, or are we defining a class called business? Ultimately, this is just about names. We're calling something a shop, we're calling something a business. Or, for example, for vegetation, do we want one class for tree, one class for bush, one class for herb? A herb is just a non-woody plant. Or do we have one class, bunch them all together and call them vegetation? Yep. So different classes, numbers of classes. The other thing is we can have exactly the same classes in two ontologies, two class models. But unless those classes, the definition of those classes are the same, the models are going to be slightly different. They're going to differ. So if we define a class shop, well, what is a shop? A shop, well, I mean, you might say, well, it's blindingly obvious what a shop is. Well, what about things like pop-up shops? They're very popular at the moment. Would you include them in your model of shops? Depends who you are and what the reason is, what your application is. Similarly, perhaps you went for a definition of classes that divided tree, bush, and herb. But what is the difference between a tree and a shrub? Is it the size, how big it is? Or is it the species that defines whether it's a tree or a shrub? So the same model may have trees and bushes as classes, different models may have trees and bushes as classes, but different definitions of what a tree and a bush actually is. Okay, so alternative ontologies differ in the set of classes that exist and how those classes are defined, possibly. And if there's a mismatch between two ontologies, then it can be difficult to bring those data sets together and recombine them. Oh, objects in the computer. So that's really all I've got to say about objects in sort of the real world and how we define them. So what is an object in computer science? Well, an object is they're generally defined, or they are defined as attributes plus behavior. You're combining an object is a set of attributes plus some kind of behavior that the object can do. So we're pretty familiar with attributes, hopefully now. Values, but also attributes can be a lot more complicated than just simply a numeric value or a text value in a field. Now that's a simple attribute. The person was 6'1" tall. The car was blue. But attributes can be more complicated. They can be lists of things, multi-valued attributes. They can be geography, the geographic location of places. They can be images, sound, and indeed they can be other objects in the object model. So you can have an attribute being an object being an attribute of another object. Okay? So these attributes can be quite a general list of different types of attributes. And then there is behavior. Well, behavior is new. We haven't really met behavior. Behavior is what, or not an object could do, not what an object can do, what an object can do. And these are generally often called methods. So the methods are the things that the object can do. And we'll get into what that means. It could be as simple as we can change the value of an attribute. That might be something that the object can do, change its value. But it might be a lot more complicated than that. It may basically have a huge program behind what an object can do. Now I identify, generally people say objects equals attributes plus behavior, and behaviors are defined by methods. But there's also another set of controls called events that may be defined, which are sort of a type of behavior. And events often left out of the basic object model, but I think they're quite relevant and should be included. Events are things that trigger behavior. So if we've got a model say we've got a model of people and cars and a simulation model. An event might be a car object touching a person object or something like that, which then kicks off some kind of method on the person object and the car object. The person object goes to the hospital object and has an operation object given to them or something like that. So events are things that happen that then kick off methods and behavior in an object. And by defining these, this allows us to develop complex models of the world, these things. Objects exist both in two places. This is not exactly unsurprising. We can have objects, what I've called program objects, objects that exist in memory in the computer, and they are generally, this is a crude dichotomy here. Sometimes when you're dealing with database objects, of course, they're existing in memory and things like that. But in general principle, you can think about objects in a programming language. Generally, they exist in memory. In the RAM memory, they rarely get written to disk. They might not get written to disk. But we've also got objects stored on disk, managed by a database object in an object-oriented database. So objects can exist both in programs and stored in database, which queried and managed using some kind of object-oriented database management system. Just to mention while we're on this object-orientated versus object, it's pretty much a synonym as far as I'm concerned. Some people call them object databases, some call them object-oriented databases. It's the same thing, basically. Okay. And we can also store these objects in files, maybe encoded in XML or JSON. We'll meet those mostly next year. We're going to meet XML, JSON. Basic idea is that objects exist both in databases and in programming languages, and they're pretty much the same to me. Whether they're stored on a disk or in memory, it doesn't matter. They're the same kinds of things. Why do we bother with objects? I mean, we've got the relational model. We haven't done programming yet, but you can do standard, what you could call procedural programming, where you just write normal traditional code rather than developing objects. And we'll meet this next year. I appreciate we haven't kind of done coding, much code. Well, we haven't really done any coding yet, just done SQL, which is not quite the same. So why do we bother? Well, it's a very powerful and intuitive data model. So you've been struggling, doing really well with doing your entity relationship diagram, deciding what your entities are. Well, it can be quite difficult, as you maybe appreciate, in the relational model. Something that's made up of lots and lots of different bits gets spread across lots and lots of different tables in your model, and it can be different in your relational model potentially, which makes it kind of difficult to get a grasp on some things that are in a relational database model. The object model is much more, well, there's a word for it, it's called encapsulation, and we'll meet that later on. But because everything is wrapped up in these object definitions, both the attributes and the things it can do, it's kind of more intuitively manageable, because you've got this one object, you can define what it is and what it can do, very simply. Whereas in a relational database, your objects, your high-level objects, may be spread across multiple tables and things like this, when you need to know how that is structured across those tables in order to make queries upon it. So that's one thing, is it's an intuitive and powerful model, data model. It's very good, efficient way of managing your code. Okay, I know I'm dealing with things we haven't really got to yet, but because the code to do with the objects is all embedded within the objects, it means that it avoids repetition of code throughout your system. So it's an efficient means of managing code. And you can use the objects both, you can program with procedural and normal programming in object code. We'll meet all this next year. But so these are a number of reasons why we might develop objects. But there is an upfront cost of defining your objects in the first place, defining and implementing your objects. So for very small applications, it's not worth bothering with objects. For many, many things, if you're doing a few hundred lines of code, a few thousand even, it's probably not worth bothering with objects unless you particularly want to do object development. As systems get larger and larger, the things that you're modeling become larger and more complex, and the number of people involved in developing systems get larger, the benefits of the object model become larger and larger and larger. So for many large systems, I would say very few large systems are probably being developed without objects nowadays. I'd be very surprised. So objects are underlying most of the large data, not database, but certainly programs that are written nowadays. In fact, most programming, I would say, large-scale programming is object programming now, or involves objects. Brief history, okay, doesn't very wide on the slide. Okay, what's the relationship between objects, the object model, and sort of relational model through time? Well, like the relational model, it has its origins in the late 60s, early 70s. 1967, a language called Simula, or a programming language called Simula 1967 was written, and that was the first programming language that included classes and instances. And it was for ships, and I believe it was the Norwegians or the Swedish, and they were modeling how ships explode, like you do. So that was the start of developing of objects. Then it was particularly in the 1970s, the idea was picked up by Rank Xerox at the Menlo Park in California, where they're based, and they developed a language called Smalltalk, which was the first real object-oriented program language. And they developed this Smalltalk language in a project called Dynabook, which was an attempt in the 1970s to develop the first laptop tablet computer. They never actually physically built the laptop, but this is their sort of prototype diagram for it. But they did write the programming language that they were going to use to run on this imaginary tablet, and that was called Smalltalk. Also in the 1970s, the first object databases were developed, particularly for managing network as implementations of network databases. And also the objects themselves were developed, so we could now have dynamic objects, so objects whose values, whose attributes could change through time, and the concept of inheritance was introduced. Now we'll meet inheritance in a minute. 1980s and 90s is when the objects really took off in the world, with the development in the 80s of the C++ programming language, and in the 1990s with the Java programming language. Java, and certainly Java, I'm not really familiar with C++, is a complete object programming. There is nothing but objects in Java. Many other languages like Python allow you to mix objects with non-objects, with normal programming. Java is a pure object language. And we also got the introduction in the 1980s, the late 1980s, of more advanced object or object relational databases. Things like, I don't know if any of you have come across Small World. It's a GIS that has a strong, well, it certainly used to be an important player in the sort of utilities market, water mains. My first ever job was using Small World, mapping water mains in Edinburgh. Well, first ever GIS job, I hasten to say, many jobs before that. So these became commercial products being used by large corporations in the mid-90s, late 90s. Just while I'm here, object/object relational databases. What do I mean by object or object relational databases? An object database is a database that stores objects, not surprisingly. An object relational database is objects stored in a relational database. So you've got this layer on top of your relational database which manages the objects, but the objects themselves are actually stored in a relational database underneath. And Small World was an example of that. Now in the 2000s, we've got the world of NoSQL databases. And to me, many of those are kind of object-like databases. Some of those are object-like databases. They've got object-like characteristics. So we've basically got, it's had a parallel life to the relational model. But it really, I think I looked last year at the sort of percentage, trying to get an idea of what proportion of the database market is object databases. I think it's still less than 10%, maybe 7-8% if I remember the figures right. It's very difficult to get figures for how many, how many relational databases are being used, how many object bases. So it's a significant proportion of the market, but it's not, compared with the relational data, is still a relatively minor model. But certainly, as I say, from a programming perspective, it's very important. All right, object concepts. So this is, these 5 things, 5 components, are what, to me, form the basis of the object model. And if you understand these concepts, you basically understand the object model, and it's just a question of how that object model is implemented in different databases, programming languages. So we've got classes and instances, inheritance, composition, polymorphism, and encapsulation. We'll run through these. So we've met classes and instances, but let's meet them again. Classes are, as we know, instances are the individual objects in the world, and classes are groups of those objects with methods common, that share common attributes and common methods. So, for example, here we have individual Ferrari cars, not my choice of object, but you inherit things. And we have a class called Ferrari. And basically that class is a template, provides us a template or a blueprint, or sometimes it's called a factory. In ArcGIS terms, they talk about object factories, factories that make things. And these make instances of Ferraris. So a class defines the attributes and the methods, what a thing can do, but it also allows us to create new objects, because that's how the objects are defined on the class. Very simple. So that's classes and instances. So here's a little example for our Ferrari, our class Ferrari. Maybe it has properties, attributes, color, model, horsepower, etc. Its methods might be things like start and accelerate, decelerate, turn, steer, I don't know. Events, things that happen that maybe kick methods into happening. So things like somebody presses the brake, that might be an event that then causes the method perhaps decelerate the method. Refuel, for example, might be an event. Collide might be an event. And those kick-off methods, which may then, of course, affect properties and things like that. So that's just one example of the possible properties and methods of events. Classes are not just confined to physically real things in the world. We can make classes of anything we like. Anything we can conceive of, real or abstract. So, this is Visual Basic, a programming language which you write, and this is how you build a form. This is just a simple form building thing in Visual Basic. Buttons, checkboxes, options. All the form is an object in Visual Basic. The pull-down menus, the checkboxes, these are all objects in Visual Basic. And if we go over the right-hand side here, we can see the forms button. These are the attributes of the form button. And then there is also methods, list of methods, things that we can do to a form button. We can check it, we can uncheck it, we can do things like that. So they don't have to be real things, they can also be sort of these abstract things as well. So, that's classes for us, simple as that. Now classes we relate classes to each other into what we call a class hierarchy, and this is known as inheritance. So, individual Ferraris are instances of the class Ferrari, we know that. A Ferrari is a type of car, and a car is a type of motor vehicle. So we've got a hierarchical relationship. Ferraris are cars, cars are motor vehicles. And if we think of them in the terms of classes, we've got three different classes here. We've got the class car, the class motorbike, and the class truck. Maybe subclasses of motor vehicle. A motor vehicle maybe is the superclass of cars, motorbike, and truck. The picture always makes this more informative. So here's an example of a class hierarchy in operation. So we have the class motor vehicle at the top there, and then underneath we have three types of motor vehicle: class car, class motorbike, class truck. And under car we have two types of car: class Ferrari and class Volkswagen in this case. Now the important thing about the hierarchy is that the lower classes, the subclasses in a hierarchy, inherit, hence it's called inheritance, the methods and the attributes of the higher classes. Yep. So that car inherits the attributes and the methods from motor vehicle. So does motorbike, and so does truck. Ferrari inherits the attributes defined and the methods defined in both car and in motor vehicle. So as you go down the hierarchy, lower in the hierarchy from superclasses to subclasses, you move from more general classes to more specific classes. So these are more specific things. A Ferrari and a Volkswagen is a more specific thing than the motor vehicle, which is a more general thing. So this means we only have, remember one of the reasons for object code was maintenance of code and good management of code. So for the shared attributes, the attributes that are shared and the methods that are shared across all these subclasses, and the subclass hierarchy may be huge under here, we only define we've defined the shared attributes and methods only once at the relevant level of class, at the relevant hierarchical level. I've also got two different types of classes highlighted here. I've got what we call abstract classes and instantiable classes. Instantiable. So what are these? Well, some classes, insatiable. These ones, anyway, the green ones, insatiable classes. They are ones where you can create instances from those classes. So there is such a thing as a Ferrari. We can create instances of Ferraris. We can create instances of Volkswagens. But what does it, in this hierarchy, as defined, we can't produce instances of these abstract classes because they're abstract. What is a car? Well, we can't create an instance of a car in this model because real cars are more than just the subset of things defined as car. We can create Ferraris, we can create Volkswagens, but we can't create generic cars under this model. We can't create generic trucks. We can't create instances of motor vehicles. And this is to do with control. It controls what the user can and can't create. Okay? Somebody's defined these classes and these objects. These are class objects. And part of the definition, the ontological definition, is that you can create instantiable classes, but you can't create instances from abstract classes. That is part of the model, part of the ontology. Here's an example. Yeah, that about sums up my vehicle. Yeah. So subclasses inherit attributes and methods from their superclasses. Here's an example. Here's my truck. It's got an ID, it's got a chassis number, it's got an owner, it's got a tachograph number, and it's got a maximum load in kilograms. Here's my class model here. So we've got the truck and we've got the motor vehicle. So at the motor vehicle level, I've got defined the vehicle ID. All motor vehicles have an ID. A chassis number. All vehicles have a chassis number. All vehicles have an owner. So these are applicable to cars, trucks, motorbikes, all subclasses of motor vehicle. So trucks, because they have tachographs, if you catch it. Everyone know what a tachograph is? It's the machinery that says whether the truck is being driven or not, so it records how many hours a vehicle's being used for sort of commercial drivers and things like that to make sure they're not driving too long and too fast, I think. So a truck has a tachograph which has an ID and it also has a maximum load. So my truck, the first three attributes are inherited from the motor vehicle class. The second two are inherited from the truck class. So that's inheritance. Composition, and we'll go through the 5 things and then we'll have a little break and then we'll do the Python afterwards. Composition. Things are made of other things. A car has, I can't even read these, it has door panels, drive shafts, headlamps, and one of the things it has in an engine. And the car is made up or comprised or is composed of these various different other objects, and this is called composition. So an engine has a relationship of part of with a car. And this is basically saying that so here we have car. One of the properties, one of the attributes of the car is its colour. The other property is its engine. So this is an attribute that is another object. This is what composition is. So in this case, the attribute property is not a text string that tells me it's some kind of, I don't know, engines. I don't know very little about engines, but that it's a 1.8 diesel turbo something or other. Instead, we have an object with a part of relationship to another object called an engine, which has the properties cylinder, piston, all the other attributes and methods that an engine might have. And in this case, we have a one-to-one relationship between the car and the part. So each car only ever has one engine. There's a cardinality relationship here, just like we had with entities. But it's a part of relationship. But we can have also one-to-n components. So I've no idea, this is some footy competition or something. So in this case, the objects are maybe the groups, the instances. So group A is an instance of the group. And in this case, each group has 4 component teams. It's made up of, has 4 parts, your components. So we've got a 1-to-4 relationship in this case between the group objects and the team objects in this competition. So we can define relationships just like we can with cardinality between entities in a relational model. Polymorphism. Polymorphism is the idea of one interface but many behaviours. And the behaviour, or the method behaviour, is dependent on the class of the object that it's being run on, or that it's related to. So we know that subclasses inherit the property of methods from their superclass. Yeah? But superclass methods may not always be appropriate for subclasses. The world is complex. The world is not hierarchical. Hierarchies are great ways of arranging things to make them manageable, but they don't necessarily represent the complexity of the world as it actually is. So in this example, in the class motor vehicle, I have a method defined cornering stability. So every time you drive your object, your motor vehicle object, round the corner, the cornering stability method gets fired, perhaps by the degree on turn on the wheel or something like that through an event, and it calculates whether you're going to tip over or not. Now, most vehicles have four wheels. Trucks, cars, I don't know what else, we might have buses. You know, most vehicles probably have four wheels. So at the motor vehicle level, we can define a method for cornering stability for four-wheeled vehicles, because almost all the classes underneath are four-wheeled vehicles. So therefore we can use the same class, same method for all our four-wheeled vehicles. That's great. However, motorbikes are an exception because they have two wheels, and therefore the four-wheel stability algorithm is no good. But it's a subclass of motor vehicle, so it's inheriting this four-wheeled stability method from the class above. But what we can do is we can define the method again at the class motorbike level. So we've got exactly the same named method, but we've got one version at the motor vehicle level and one version at the motorbike level. And this is sometimes called overriding. So if you ever heard of overriding methods, this is an example of an overriding method. So when a car goes round a corner, what happens is it looks up the hierarchy from the class car, which it's an instance of, or you can get a Ferrari, let's say Ferrari. So we've got an instance of our Ferrari. It goes round the corner. Does it turn over or not? Well, it looks as its own class, Ferrari. Does that have a cornering stability algorithm? No. So it looks up the next one, to car. Does that have a cornering stability algorithm? No. So it looks up the next to the motor vehicle one, and it finds the method, and it uses that method. Motorbike goes round a corner. Maybe it's a, I don't know, what are they, Norton. It's a Norton motorbike. It goes round the corner. It looks into Norton class, can't find a method for cornering stability. So it looks up the class to motorbike, finds a cornering stability algorithm, which is the two-wheel version. It fires that one and it uses that one. It doesn't bother going further up the hierarchy to find the four-wheel vehicle hierarchy. So that's polymorphism. So whenever you get an instance of a vehicle and it's going around a corner and you need to find the color, you can fire the method cornering stability, and that will either run the two-wheel algorithm or the four-wheel algorithm depending on what class it is. One interface, one method, cornering stability, many behaviors depending on the class, what class your object is. This is all sort of almost an aside, this one. Some programming languages such as VB, Visual Basic, .NET, which is one of the environments in which, well, one of the environments I develop ARC objects programs in, ARC objects being the underlying object model underlying ArcGIS. That works solely on things called interfaces, which is probably unnecessary in this lecture, really. But it's kind of it's an interesting way to see how these how we do different programming languages deal with class definitions in different ways. So in Arc objects, you never actually use classes at all. Classes, they exist, but they're hidden underneath things called interfaces. And what interfaces are effectively the methods. They are sort of the methods on their own without any object definition sort of behind them, so to speak. Okay, so it's a bit complicated. So I've got a class motor vehicle that has a method move that inputs, has two values that go input. Maybe it's speed and it's direction or something like that. I also have a class animal that moves, which similarly has two inputs, speed and direction. These methods, move, may be implemented in the classes very differently. So the move algorithm for an animal may be very different from the move algorithm from the vehicle, despite the fact they have the same inputs, a direction and a distance. Perhaps it depends on what the terrain is that they're being told to move across. Maybe a motor vehicle will only move if it's on a road, whereas an animal can move across a landscape. But they both move. And rather than calling the method move from the class, the instance of the class, in Visual Basic and in interface programming, what you do is you create something called an interface, which is separate onto the class, and then you call that interface on the instance rather than the class. Okay. It's a bit complicated, but it's another way, a different way of implementing polymorphism in a different language. Really, okay, I can look at there's some very quizzical looks there. I can understand that. I have trouble understanding this myself, and I use it. I use it on a regular basis. Basically, it's kind of creating this extra thing on top. So if you want to move anything, you use the move interface, and that is because it's linked to a class. It then knows how to implement the class algorithm. The take-home story is that methods are implemented in different languages in slightly different ways, I think is what the message that I'm asking you to take home. This is the final concept of the class model, the object model. We'll have a break after this. And this is the idea of encapsulation. So encapsulation is the idea, the theoretical and practical idea, that the user doesn't need to know how an object works. All they need to know is how to work the object. So here's our cat. Okay, we can stroke the cat. Which is something we can see, it's the outside, we're familiar, we can stroke the cat, and maybe the cat kicks off the purrer. But we don't need to know the mechanics of how the purrer works, we just need to know that we stroke the cat to make the purrer work. We know that if we get a ball of wool out, a bit of string, and we dangle it in front of the cat, that's perhaps going to implement the pouncer, which result in the wool tangler being a method being implemented, but we don't need to know anything about that. We just need to know that we can play with the cat with a string. So encapsulation is hiding information. That's kind of its definition. And it's the principle of separating the user from the details of how something works, the object works. So, well, what's the practical endpoint of that? Well, what it means is that an object or a class, the object class, must be fully described by its class code. So its class code must fully define the object. You shouldn't be able to do anything with an object, with an instance of an object, except through the code that defines its class. Yep. If that's the case, we can only use the methods to interact with the class. We can't interact with the class or the instance of the class in any way but through its methods. And that means that we're separated from what's going on in the methods. We just need to know the methods and how to parameterize them, not how they actually work. Defined methods and interfaces. And these interfaces encapsulate common polymorphic data. Right. Okay, let's have a break, and then we'll look at objects in Python. Any questions about the object model before we? Yeah. Yep. Obviously, the slides are up on Study Space, but yeah. Any questions on the? Everyone happy with the object model? It's kind of hard to get your head around. I felt when I was taught first met the object model, which was I suppose in the late 80s, early 90s. No, it must be the early 90s. I really didn't understand it at all, which is one of the reasons why I've got this, decided to do this practical in Python, so hopefully you can get a physical grip on what these objects actually are. Okay, so let's take 10 minutes and then we'll meet back for some